Okay, so there's the usual homework list, right? I haven't added anything for a while, but we're um, just about prepared to, I think, do all of these homeworks. Maybe after the notes today, we'll be ready to. But the ones that are immediately due are the this homework. About 2/3 of the people have worked on that homework. But it's due tonight, so we want to try to finish that one in class today with 100%. Okay, no reason not to get 100% since you can, ask for a new question, right? If you don't get it right in the first 3 attempts, and you've got Taylor and me here to answer questions, so you get 100 on that one, and then this quiz. Harder to get 100 on a quiz, right? But that quiz, it was due tonight, but I moved it back slightly. So when we finish that homework, we want to also make a start on that quiz, right? Okay? So that we can at least get some score in the grade book today, and then you can finish it. You can take it again, right? And improve your score if you need to a little bit later on. If you're past these two things, you can also work on these homeworks, I think. We will have discussed, I think, most of the things in these homeworks, if not all of them, by the end of the class today, or by the end of the lecture today. I can't remember exactly the sequence of problems in those two homeworks, but we'll be pretty close to having discussed all of those things, okay, from those Chapter 2 homeworks. So you can work on those too, all right, and get started on those. Does anybody have questions right now on any of these homeworks? I passed back now those activities that we did in class. So I just wanted to see if you turned that in, right? Okay, everyone was working on those pretty diligently. So, but I did enter a score in the grade book for those. Okay, if you were here to turn those in, all right. So you do have a score that contributed to your average there a little bit in my math lab. And we'll go over those here in just a second. Let's remind ourselves, though, we had this example that we didn't work through last time. So let's try this one. Just to remind ourselves of what we were discussing last time, which was basically practicing using interval notation. But one place where you get to use interval notation a lot is describing where functions are increasing or decreasing if you're dealing with functions that are not linear functions. So most of the examples of functions that we've been using in class here through the end of Chapter 2 are going to be linear functions, but we'll eventually look at functions that aren't linear functions, so they'll have a lot more wiggles in them. And they'll have places there where the function's increasing and places where the function is decreasing, right? And so using interval notation, what we want to do in this problem is, it's like previous examples. We want to write down where this function is increasing, and then also where this function is decreasing, and possibly where it's constant. Let's give a name to this function. Let's call it f. Our favorite name for functions there. So what I'd like you to write down there, just as a little a recall practice here, is write down for what set, right, the function f is increasing, and then for what, so you'll fill in the blank here, kind of, right, and then for what set is the function decreasing, and then where it's constant, neither increasing nor decreasing, if that's the case for the function f. We mentioned last time that's kind of an unusual case, but sometimes it happens, right, that a function is neither increasing nor decreasing, all right? So see if you can fill in those blanks. And remember, we want to fill this in using interval notation, right? That special type of set notation, right, that we learned last time, right? And keep in mind, right, when you write down where a function is increasing or decreasing, you always do that in terms of the x-axis, right? So you're going to give your answer there in terms of the x-axis. You don't have to recopy the graph there in your notes, all right? The notes are posted, right, on the Blackboard page, so you can find this graph later if you need it. Just look at that, right, and then just try to fill in those blanks here looking at this picture. If you start recopying the graph, it'll take us forever here to get through this little activity, and we don't want to take that long, all right? This is just a little bit of recalling what we talked about last time, all right? Which is in this homework that's due tonight. So take 3 or 4 minutes there, maybe 4 minutes at most there to fill in those blanks, okay? Let's scroll up a little bit so you can see the whole graph there. Is that pretty easy? Most of this is one of the great things about graphs, right? It sometimes can make questions like this one much easier to answer, at least to get estimates, all right? A question like this one, if you do not have the graph of this function, if you only had the formula for this function, and you weren't able to make a graph of this function f, this question would be really difficult to answer just from the formula, okay? But that's a process then that's taken up in calculus. This is one of the things that calculus will study is how can you determine where a function is increasing or decreasing without the graph, just from the formula itself, okay? So just with pencil and paper without drawing a picture of it. All right, so we run out. Yeah, well, oops. I'll give you a few more seconds there. So everyone make sure they've got something written down, right, okay? Give it your best shot there, okay? And we'll ask someone or some people here to share their answers. One thing I didn't ask now is, but I could have, is what is the domain of this function, at least the way it's graphed, right? What does it appear that the domain of this function is? So what's the extent of that function, right, along the x-axis? No, you're not guessing. No, we're not guessing here. Okay, right? The way it's drawn, right? What would we assume there is the domain? Hmm? That's right, negative infinity to infinity. Danny, why'd you say that? Right, so on the left-hand side, the graph is just going up here, right? And but it's not cut off, right, in any way. So you don't have an open or closed dot here. So you have to assume that this on the left, this pattern is just going to continue, okay? If that pattern wasn't going to continue, whoever illustrated that graph, whoever drew that graph, should have indicated that, okay? So it looks like that pattern is just going to continue. So that it looks like eventually that curve is going to extend all the way to the left. It'll take a little while, right? But eventually that curve will extend all the way to the left on the x-axis. And so that means the domain starts at minus infinity, right? Remember, domain is associated with the x-axis, right? And the same thing is happening on the right, correct? This graph is not cut off on the right, so we have to assume that curve is going to continue down like this, which means eventually that curve will extend all the way to the left, right, below the x-axis. So, so the domain extends to positive infinity. So you had it right there. It's minus infinity to infinity. Danny, how do we write that in interval notation? Parentheses, right? And then what? Minus infinity, which looks like this, right? Okay. And then what? What? To positive infinity, that's right, okay? So you write it like this, yeah. That's interval notation for negative infinity to positive infinity. In words, that would be all real numbers, right? So the domain there is all real numbers. That's also going to be the range as well, okay? The range of this function will also turn out to be all real numbers when you look at the graph there. So we have a nice domain and range, really big, right? We can use any number for input, and so we can use any number x as input, right, to this function, and we'll get any number also as output eventually from this function. All right, so but that wasn't the question we asked, right? We want to know first, where is it increasing? So if remember, you're always thinking of yourself as going from left to right, okay? So there's a little bit of cultural bias here in that. And the way we read graphs, we read from left to right, okay? You know, some cultures read from right to left, right? But we usually read from left to right, so that's how we're going to interpret the graph, is from left to right. So from left to right, you know, as you're moving across the coordinate system there, sometimes the graph's going up, right, and sometimes the graph is going down. So in answering where it's increasing, we want to write where is it going up. Geo, where is it increasing? So you were here last time, so you saw this whole lecture. So where is this function increasing? Where is this curve increasing?
On the right side of the graph, where it's like going up.
Yeah, on the right side of the graph, right? It's going up. So when you say on the right side, okay? This is the right side. Am I? Yeah, this is the right side?
Yes.
Okay, all right. But as you move from left to right there, Geo, I don't see it going up. It looks to me like it's never going up here on the right-hand side, right? On the right-hand side, it looks like it's always, well, not going up, right? Okay. Again, we're thinking of ourselves as moving from left to right, all right? Okay. So as you're moving from left to right, where is it going up, increasing? So starting here at minus 3, right? Yeah, okay. So starting there at minus 3 and going over to where? Because it's not always going up, right? -1, that's right, yeah. So it's increasing from minus 3 to minus 1. And remember, you're going to give your explanation in terms of the x-axis. So you said that right. It starts increasing at minus 3, and it continues increasing until x equals minus 1, right? You don't want to say it's increasing from 0 up to 3. That is what's happening on the y-axis, right? It's going from 0 on the y-axis to 3 on the y-axis. But that's not the way you give your description, right? You say it's increasing from x equals minus 3 to x equals minus 1, all right? Now, how do we write that? So that's a set of numbers, right, from minus 3 to minus 1. How do we write that in the interval notation, Geo, that set of numbers between minus 3 and minus 1? Negative 3, comma,
negative 1.
-1, right? But you have to surround this. You have to group these together. So what do we put on the left or the right there?
Brackets.
Yeah, we put either brackets or what's the other possibility there?
The commas like that.
That's parenthesis, right? Okay, yeah, all right. So either brackets or parentheses. And remember, there is a difference, right, between using brackets or parentheses, right? It's a subtle difference. With brackets, that means that the boundary value, these are the boundary values for the set, right? With brackets, you mean the boundary values are included in the set. But if you put parentheses, you mean the boundary values are not included in the set. Well, remember, when we're describing where a function is increasing or decreasing, whether you should include the boundary values in the set is a little bit ambiguous, all right? So I usually include them, but in your homework, they may not include them. They may want parentheses there. So you have to be careful when you're answering the homeworks what they're expecting, all right? All right, so there it is. There's where it's increasing, all right? So now where it's decreasing is trickier because it's decreasing in multiple spots, right? Okay, so we have a little bit more work to do there where it's decreasing. Amber, where is that thing decreasing? So where is that curve decreasing as you're moving from left to right? Okay, so as you're moving from left to right, where is the curve falling? Um, yeah, so as we're moving from left to right, what's happening over here on the far left? As you're moving from left to right? Is it going down or going up? It's going down. That's right. Yeah, it's going down. Right. See, this part of the curve is going down. So that is decreasing. Right. It's decreasing there. So what is that set? Where does it start decreasing, Amber? Over here on the left. Where does it start decreasing? Yeah, on the x-axis. Where does it start decreasing, though? Negative infinity, that's right. It's going to be decreasing all the way from the start of the x-axis, right, to here. And we already said the domain starts at minus infinity. So it starts decreasing at minus infinity in the x-axis. And it stops decreasing, though, and turns around where, Amber? So this pattern continues until you get to where on the x-axis? -3, right, okay, because G already told us that's where it starts increasing, right, okay? All right, so our first set where it's decreasing is, you told me, minus infinity to -3. So how can I write that down with, how can I write that down, Amber? Amber, how can I write that down with set notation? Okay, all right, so where does it, so how do you write minus infinity to -3? Negative infinity, right, and then what? Comma, -3, right, okay? But now we have to put brackets or parentheses there, right? You cannot put bracket beside minus infinity. That, you can never include that in the set. That's not even a number. And then, beside the -3, well, just by agreement, where when it's increasing or decreasing, I'm going to use a bracket. But now we're not through, Amber, because it's going to decrease elsewhere. Where else does it decrease as you're moving from left to right, okay? So this part is increasing, right? So it's not that piece, but where does it start falling again? At where? The 2 here? I think it's decreasing before there. Yeah, where does it start decreasing? On the x-axis, where does it start? -1, right, and it continues decreasing until you get where? Right here, which is at 1, right? So you have to write that set down also, -1 to 1, okay? And then you write that down using interval notation, -1, comma 1, all right? Yeah, it's decreasing at 2 different times. And there's a third place where it's decreasing too. Because, yeah, what happens on the far right here? This part also decreasing, right? So where does that start? What? 3, right. Yeah, I think it starts decreasing at 3, right. Okay. That's a little bit hard to see, but that would be our estimate. I think it's going to start decreasing there at 3. And how long does that continue decreasing? Infinity, right. Okay. So see, we have 3 separate sets where it's decreasing. You're going to have to combine those sets into one answer, and the way you combine sets is by using, in math, it's called the union of the sets. That's how you combine sets. So you indicate that notationally by putting that little, it's kind of like a U, but it's a little stylized U there between the sets, and that just means we're putting all these sets together to form one big set. So there's the big set where this function is decreasing, okay? So you get kind of a complicated answer there, all right? Yeah, or 2. Infinities can never have brackets, that's right, because that's not really a number. Yeah, we just use that notation to indicate indefinite, right, okay? That the set continues indefinitely, either to the right or the left. Now, this... Yeah, you may lose a little bit. It wouldn't be completely wrong, all right? Now, this function is unusual because there is a place where it's constant. Constant means neither increasing nor decreasing, so that means it's perfectly flat. Where is it perfectly flat? 1 to 3, right? It's the rest of the domain, right? This is everything except this little piece right here from 1 to 3. So this function is constant, right, from 1 to 3. So just fill that in. It either has to be increasing, decreasing, or constant. So when you combine all those sets, you have to end up with the entire domain of the function, because it's either got to be doing one thing or the other everywhere, okay? So when you put these 3 sets together, you should get the domain, but that's what happens here. You combine all of these sets, and that's all real numbers, or is in one of those 3 places, okay? All right, I think this is probably trickier than any of your homework problems for increasing and decreasing in that 1.4 part 2 or whatever that was, okay? All right. All right, so let's go back now, and that was a little detour there, but most of our focus here is on, for the time being, is on straight lines, okay? And so let's look at, not this example, but let's look at our activity that we all finished in class last time, because you got a lot of good practice there last time with writing down formulas for straight lines, which is what we've been discussing. Okay, I want someone to share with me the lines that they drew. So I just want you to bring them up and show the class. Okay, and then we're going to talk about how we wrote down the formulas for those lines, right? Okay, that you guys graphed, the fitting lines, right, for your data sets. That was the focus of activity 4. Some of y'all got through all of that. Some of you got half of it done. So, but we want to fill in the answers for you. All right. So, Ben, would you show us? Would you just show us? You're just going to show us what you the graphs that you drew, right? Yeah. So the 3. Yeah, no, we're going to look at both of them there, right? Okay. All right, let me see if I can get that whole thing. All right, there it is. All right, so there was problem 2 from activity 3. Remember, this is the line that fit that. That was the amount of waste generated, right? The amount of trash generated, right? In some year. I think this was elapsed years from 1900, right? Okay, and so we had these we had these data points, right? We knew for certain years the amount of trash that was being generated, right? And then what we were trying to do in this activity was make some projections about the future, correct? Okay, and so. Right. Okay. And so there's the fitting line that that Ben drew for that particular data set. Okay, that looks pretty good, right? Okay, I would say perfectly reasonable fitting line there, right? It certainly looks like it matches that set of points. Okay, but remember now you're drawing these by hand. And so different people may see the set of points slightly differently, and they may draw slightly different fitting lines. Okay, and so but we can use that fitting line, right? And y'all did this right to make predictions about the future. So one thing we were trying to do was predict the amount of trash that was being generated or is going to be generated, right, next year in 2020. And so using the fitting line, there's the point on the fitting line, on Ben's fitting line that corresponds to 2020, right? And the output for that point was, what did you write down for that, Ben? Do you remember? 275, okay? Oh, I think you missed a little bit your fitting line, didn't you, right? Because where's, in this graph, where's 275? It's right there, isn't it? But that point's a little bit above. Isn't that 275 right there?
It's like a little bit above this dotted line.
Right, a little bit above this dotted line. So what I'm saying is the coordinates for that point, obviously the x-coordinate is 120, right? But the y-coordinate I don't think is 275 because that's a little bit too high, isn't it? Because 275 is right there. So this would be somewhere between 275 and 300, right? Okay, it would be a better estimate. Let's try writing down what we think the coordinates for that point are. So it looks like this point here on your line, right, where you've got the dot, because that's definitely on the line. So that's 120, and then so that's somewhere between 275 and 300. So what does that look like to you? Maybe 280 something? 285? Yeah, that might be maybe a little bit closer estimate there, right? Okay. So it looks like Ben's fitting line there goes through this point, 120, 285, and so your projection based on your fitting line for the year 2020 is 285, right? Okay. But now, if we want to use the same fitting line, right, Ben, to make projections beyond 2020, we're in trouble here, right? But just because of the way the graph is drawn, correct? Okay, because we just can't see what's happening here in past 2020, right? On this graph. So, of course, the way we can fix that problem is to turn that line into a formula. All right. So functions have graphs. But functions also have formulas, right? Okay, and so if we can write down the formula for that function, then we can use that formula actually to project really any year in the future that we like, right? Including, for instance, 2030, correct? Okay, so that was our goal in the next on the next activity, was to write down the formula for that line. Okay, but now we know how to do this, right? Okay. So now we know how to write down the formula for that line. All right, so hang on there, Ben, because I'm going to get someone to tell us those steps. Kevin, okay? So I want you just to describe in general what steps you go through to write down the formula for any line, well, including Ben's line here, right? Okay. So in general, what would you do to write down a formula for a line like this one? What do you need? What information do you need, and then what steps do you need to go through? You need 2 points, right? Okay. So you need 2 points on the line because you're going to use those 2 points to calculate what? The slope, right. So that's step one, right? Find 2 points on the line, however you can find them, right? So that you can calculate the slope. Well, we've got 1 point on Ben's fitting line here, right? 120 and 285. So we need to pick another point off of this line. Ben, what's another point on your line that you can estimate? You may not get it perfect, but at least that you can estimate there. 95 and 200. Is this 95? And then right up there, yeah, that's pretty darn close to 200, right? That point right there. Okay. Oh, all right. So that's perfect. So 95 then and 200. All right, Kevin. So there's the 2 points that Ben has located on his line, right? And you said we need to calculate the slope. So how do I calculate the slope then? Right, y2 minus y1, right, over, yeah, x2 minus x1, right. So let's fill in the values here. What's y2 and y1 in this case? Mm-hmm. Yeah, there's your 2 points, right? What? Yeah, so that's fine. Okay. Perfect. Right. 95, right. Okay. Great. So let's see what that works out to be. That's going to be 85 over 25, right? And now we have to just kind of simplify that, okay? Let's see, 85 over 25. I can divide 5 into both of those things, and I come out with 17 over 5, and I think that's 3.4, okay? So there is our estimate for the slope there for that fitting line. It's 3.4. That's step one now, Kevin. So now what do I do with the slope to finish writing down the formula? Oh, I see. So you're going to use the this form for the equation of the line. That's called the slope-intercept form. So you know the slope, so you can fill in the slope, right? And then you're left with wondering what the y-intercept is, which you cannot see in this picture, by the way. This is not the y-intercept, because this is 60 on the x-axis, not 0 on the x-axis. But that's okay, Kevin. You said, how do I find it? So which one do you want to plug in? Because we know 2. 200. Yeah, 3.4 times 95 plus. Yeah, and then you just solve for B, right? So B would be equal to 200 minus 3.4 times 95, and then we need our calculator to tell us what 3.4 times 95 is, right? And then subtract that from 200. Can someone do that calculation for me there, who has their calculator out? 3.4 times 95, and you're going to subtract that from 200, right? So you're going to get a negative value here. What now? Negative 123? Ah, there we go. Okay. So if you continue this picture over to the far left here, you're going to get eventually a y-intercept of minus 123. So there's our formula. Y is equal to 3.4x minus 123. That's the formula for Ben's fitting line, okay? And now we can use that formula to predict any year that we like, right? Just by plugging in a different year for X. So if you wanted to make a prediction about 2030, just plug in 130 for x. If you want to make a prediction about 2040, you just plug in 140 for x, right? Okay, and so forth. So did y'all get an equation similar to this one? Did y'all get a similar slope? Something close to 3.4? What did you get, Uni? 3.5, okay, a little bit above 3.4. Anybody else get something different? You got 4.5? Okay, well, that's pretty high, okay? So your line was really, your line must have been really steep there, all right? Okay. What'd you get, Leslie? 3, just 3 for the slope? Yeah, so 3, all right? Okay, so somewhere there around what Ben got right for slope, okay? See, different people there are going to get slightly different, going to draw slightly different fitting lines, and they're going to estimate points slightly different, and so they're going to get slightly different equations, right, for their fitting line. There's another way now, a faster way, remember though, maybe it's faster, of writing down the equation for the line really quickly. Once you have calculated the slope, you do not have to go through this process of solving for the y-intercept. You can also write down the formula for the line using the slope and one of the 2 points that you have, like this, right? It's y equal to the slope, which is 3.4, times x minus the x-coordinate of one of the points. So you can use either of these 2 points. Let's try this one. So x minus 95, and then you just add on the y-coordinate for that same point. So 200. That is that's going to end up being exactly the same equation. Looks different, but these 2 equations are really equivalent to one another. So see, that was real fast, right? Because we didn't have to solve for the y-intercept. But it's really the same equation. So remember, this is called point-slope form. If you know the slope and 1 point on the line, you can write down the formula for the line. This is slope-intercept form. If you know the slope and the y-intercept, you can also write down the equation or the formula for the line. Okay? All right, perfect. All right, thanks, Ben. Okay, I want somebody else. All right, so let's look at the second one now, because let's see what happened with that process. All right. So on the second line, Chris, can you show us your lines for the not the trash, but the global warming, right? Yeah, you just have to show them to us. So. Nice, right? Okay, so there are the two fitting lines that Chris drew. This was the fitting line for if we considered all of the points, right? Okay, starting with whatever that first year is, 1860 or something, right? Okay, and then the second fitting line, if we look at just what's been happening more recently, so that would be the global temperature starting there at 1950, which is the last year, 150. Okay, all right. So what I ask you to do, I think, in Activity 4 is let's try to write down the formula for this second fitting line. Okay, the one that we just include the more recent temperature data. All right. So looks like you've gone through that process very nicely here, right? Because what did you do there? It's clear you picked off what?
The Y's and the X's.
Well, yeah.
Or like 2 points on the
2 points on the line, right? So you picked off there 2 points on the line. So you identified 150 and 13.7. Can y'all read that? That's 150 and 13.7. Okay, and then your second point was up here, which is 214.3. Okay, and you even labeled them nicely. So you called this X1, Y1, and you called this one X2, Y2, right? Okay, so once you got the 2 points, you must have then calculated what?
The slope.
The slope, right? Okay, yeah. So do you have that calculation there?
Yeah, I should.
Yeah, that's the first one though, right? Okay. Oh, so you ended up with 0.015. I think you used slightly different. I think you used slightly different points there. Um, let's use these 2 points. So 14.3 and 13.7. So the slope there would be right 14.3 minus 13.7 over 200 minus 150. So that's.
I put 210 instead of 200.
Yeah, you use slightly different points, right? And then that's 0.6 over 50, and we have to figure out what 0.6 divided by 50 is, right? Okay. What is 0.6 divided by 50?
Danny?
0.012.
You got it?
What? 0.012? Okay, all right. So using these points, we get a slope of about 0.012. Okay, right? And now, so once you have got your estimated slope right for your fitting line, then it's very easy to write down the formula for the fitting line because you can use one of your points and the point slope formula. So in the point slope formula, you write y is equal to the slope, 0.012, times x minus the x coordinate of one of your points. So let's use this one, 150. And then just add on the y coordinate, which is, in this case, 13.7. So there it is. There's the equation for that fitting line. Okay, see how easy that was to write down once you knew the slope? And now you can use, of course, that formula to predict any time into the future, right, that you want, just by plugging in now different values for x, right? Okay, so we don't have to, by using the formula, we can project indefinitely into the future. Not that that's really a good idea, because the further we go into the future, our predictions are going to get less reliable. No, you don't have to change that, right? That's fine too. Okay, you just did slightly different points, right? Okay. What now? No, it's just we picked different points, so we got maybe a slightly different equation. Okay. All right. Now look. So one thing y'all were, and you just noticed it here. One thing y'all were questioning me about last time is, wow, everybody was drawing different fitting lines, right? Okay, and people were picking the points off the fitting line slightly differently, okay, right? People were picking the points off the fitting line slightly differently. So we all came up with slightly different answers, right? Okay, so that's a little bit, that's okay, but that's a little bit annoying. So so how can we make things a little bit more uniform, right? Is there some sort of process we can use to determine what the correct fitting line is, right, without having to just eyeball it? Is there a process we can use to determine what the correct fitting line is, so that we would all have an agreement about what the formula for the correct fitting line is, right? And the answer is, well, of course there is, right? Okay, this is mathematics. So we definitely do have a process, right, for determining a single fitting line, single best fitting line for a set of points, okay? Actually, well, let me not say what I was going to say, all right? So I'm going to show you now how we can use, I want to show you now how we can use technology, okay, how we can use technology now to help us with this, process, okay, of determining a single fitting line, okay, the single best fitting line for a set of data points, okay. All right, so if you look in your on My Math Lab and you go to the course home, all right. So I'm in the instructor view, but when we go here to the student view, okay, right at the top, okay, right at the top there are some announcements. One, of course, is the announcement for the Math Center, right, the tutoring center, all right. But above there, I've put in a couple of other announcements there, and these announcements there have links to a tool you can use. Well, actually, a couple of tools you can use for different purposes. This first tool we're not going to look at immediately. That's just a screen that will help you graph a function, just a function in general, okay? But it's the second announcement that we're interested in, okay? Because this is the tool that we can use to draw a fitting line for a set of points, okay? So let me open that, and you can see here what it looks like. And it's very easy to use, okay? All right. All you have to do is fill in the values in this. All you have to do is fill in the values in this table, okay? So your x and y values, all right? And then the screen here, the computer, this program called Desmos, will automatically generate for you what is considered to be mathematically the most accurate or the best representation, the best fitting line for that set of data, okay? And it will also nicely tell you the formula for that fitting line as well, okay? If you scroll down here a little bit, it will tell you the slope and also the y-intercept, okay? So it'll give you the formula in slope-intercept form, all right? Again, all you have to do is just change the values there in that table. All right, let's try this now for for some of that global warming data. Okay, we're going to have to actually enter the coordinates for the points. So since we don't have that data printed out, okay, we'll have to sort of guess at the coordinates for these points, all right? But let's come to some agreement what we think the coordinates for those points are from the global warming data, right? From the global warming data, okay? But beginning with 1950, okay? So we have there, what, about 7 or 8 points, right, okay? Of global data there beginning with 1950, and I just want you to estimate there for me what the coordinates for those points are, right? So I can enter those coordinates into my table here, okay? All right, so what's our first x coordinate? What now? No. For remember, yeah, that's right. We only want to do the problem that y'all did in the activity. What? 150, right? Okay. So 150, and what's the matching temperature there? So there you're going to have to give me a good estimate because we don't have the actual 13.7. All right. Let's try the next one there. So what is that, 160? And 13.9. We all have to be in agreement with this, so y'all have to read it off for me, okay? Does 13.9 look right? Okay, all right. What's next there then? Is it 170? So that's 1970. Same thing? 13.9? All right, so then does it keep going here? 180, What was the global average temperature in 1980? What now? 14.2. What about 1990? 14.3. Next year is 200. Same thing? So 14.3 again. When you run out of, if you run out of slots in the table, you can just hit enter, and it will just generate for you another row in the table. So what's next there? 210. And what was it in 2010? 14.6. And so I'm hitting enter there, right? And then this is the odd one, right? What is this? 217 or something? It's not quite 220, right? Because what's the x-coordinate of that last point? The x-coordinate, though. Mm-hmm. 215? Well, I can't go by tens because it's not 2020 yet, Montel, so I don't know the global average, right? So I took the last available value there, which looks like it's 217, maybe? I think it was 217. I think that's the last year. And what does it look like the global average temperature was then? 14 point what? 7? There we go. Okay. So there is the, now we don't see the picture, all right, so that may be a little bit disconcerting what happened to the picture, but it's obvious what happened to the picture there. Why are we not seeing anything? That's right, because we don't have the correct what? What's this called? What do we need to fix here? Begins with a G. Y'all did this on test 1, right? Okay. I don't remember ever saying the word gradient in class. Okay, right? So what? Graphing window. Don't remember that term, graphing window, right? Okay. I didn't hear you say that. You did, right? So it's graphing window, right? Okay. So wrong graphing window here, right? The correct graphing window, we'd look at our data, right? So it looks like it would start at something like 150 and go up to maybe 220, right? Okay. And then we would have to also change the y-axis, correct? Okay, to match these values. Y'all practiced that on test number 1. Y'all actually were pretty good at that, right? Okay. So we'll fix that graphing window in a minute. But there, look, Chris, there is the official formula for the fitting line. Okay, Chris? Yeah, there's the official. I hope you're texting someone about math. Is that true? No. Okay. All right. Yeah. All right. Well. All right. So in that case, put your phone away, right? Because I want you to look at this, right? There is the formula for the official best, quote unquote, fitting line for this set of data, okay? What would the slope end up being there? There it is right there, okay? So the M, right? M stands for slope. So this is what? 0.014. You had 0.012, so that was pretty good, right? Okay? And I don't know what, we never solved for your y-intercept, but the best fitting line's y-intercept is something like 11 and a half, okay, 11.54, right? So, the computer-generated fitting line is 0.014x, right, approximately, plus 11.54 about, okay, right? Oh, let's see a picture of this. So let's see a picture. So we said, right, we're going to have to change the graphing window, right? Okay, we don't have the right graphing window, right, for this set of data. So what graphing window do we want to use there? Look at the x values. What do you want to use for the x window? So that we can see our plot nicely here. Jennifer. What? That's a nice way to answer your professor. Okay. That's not going to work. Is this your first semester in college? Yeah. Yeah, okay. All right. Don't answer like that. All right. Well, okay, so the what is, I want to know what the graphing window is for this table. So what would be an appropriate portion of the x-axis and the y-axis so that we can see this scatter plot? So I need to be able to see the x value. I want to see my points, right? Okay. So to see my point, don't coach her. To see my points, right? Okay. What portion of the x-axis would I like to see, and what portion of the y-axis would I like to see, so that I can make sure that I can see the points. See, so now I'm not seeing anything, right? Okay. But I'd like to be able to see that table of data points. We just practiced this on test 1, right? So you remember that, right? Okay. So I know you've done it before. So what portion of the x-axis there, Jennifer, would work? 140. 140, that would be a good place to start, right? Okay, up to, where could we go? 220, yeah, I think that's great. So 140 to 220 on the x-axis. And what about the y-axis there? So we got to see those y coordinates too, right? So what portion of the y-axis could we use? 13.5, yeah, that's a good start. To where? 15, yeah, okay, so I think that's good. Help me remember what you said. So it was 140 to 220, right? And then 13.5 to 15. All right, so in this software, the way you change the graphing window is go to the wrench, that's graph settings, right? And notice it will give you there settings for the X and Y graphing window. So you just have to type over those things. So you would start the X-axis there at, you told me what, 140, right? Okay. And then you would go up to 220. Okay. And then for the Y-axis, you told me what, 13.5, right? Up to, and then just go up to 15. Okay. And see, we get that nice, beautiful graph there, right? Okay. So there are all the points plotted, and there is the official best fitting line, okay, for that set of points. This process of finding the quote-unquote best fitting line that's called linear regression. So that process of going through the steps, which we didn't go through all the steps. You can do that by hand, but we had just had the computer go through the steps for us. So this process of finding that best fitting line is called linear regression. All right. Well, there it is. Okay. Does your line look like that one? Probably pretty close, right? Okay. Maybe slightly different, right? Okay, so maybe your slope was slightly different, or maybe you had the graph a little bit higher or a little bit lower. That would change the y-intercept. So maybe your y-intercept was slightly different, right? But probably pretty close to that, okay? But you don't have to, my point is here, you don't have to do this by hand and make an estimate. You can do this with this tool, all right, okay? And that way we can all agree on what the best fitting line is for a data set, okay? And we can also agree on predictions about the future from this best fitting line, okay? All right. So did y'all see where that was? Did y'all see where that was located? Right. Okay. So it's in the my math lab, right? In the course home, okay? under this announcement that says linear regression tool, you have to open that announcement, and then you just have this link, okay, and just click on that link, and it'll bring you to that screen, okay. This works great on your phone too, all right. So it works fine on the phone. It'll bring you to that screen, and then you can just change that data table, right, okay, to fit different sets of data points. That's going to show up, okay? That is going to show up in your homework assignment. In the 2.2 homework assignment, okay? And I think it's the very last problem. Let's open that problem. Okay. So there they give you a very simple data table. It's only got 5 data pairs in it, so it's easy to work with there. Just 5 data pairs, and they're going to ask you, what is the regression line? What is the best fitting line for this set of data? So to find the regression line, you're going to have to fit that with that tool, okay? Yes, it is possible to do. Yeah, you can do it with a graphing calculator. All right, okay. Huh? Right, yeah, okay. So almost all graphing calculators, if not all graphing calculators, will also compute regression lines, and they use the same process, so they're going to come up with exactly the same regression line, okay? That's right. It will come up with the what's called the linear regression best fit, okay? And it uses the same process as the computer does, because that is a standard process, so it will give you exactly the same formula for the line, okay? Yeah. Right. What's a little bit annoying now about, I had to put the link in the announcements, is that if you are working on the homework, right, so you're at this problem, right, and then you want to find that tool. So if you go to course home, unfortunately, it's going to close the homework for you. So so you'll lose the homework problem. So you'll have to work your way around that. The simple-minded way of doing that is just to write down the table, okay, and then go to this tool and fill in the values, and then come back to the homework problem, okay. But you can also do things like opening multiple tabs, all right, and you can keep both things open simultaneously. To use that, okay? But that is going to, you are going to have to be able to do that, right? Okay. Ooh, we're almost out of time. Let me just introduce now, we won't have time to talk about it, but let me just introduce now the next topic, which is still about straight lines, okay? So we're going to narrow our focus a little bit to just one particular type of straight line here for a moment. We mentioned this before, right? So here's a formula for a straight line. But if you have a linear function where the y-intercept is 0, right? The y-intercept is 0, so that gives you a very simple linear function, right? If the y-intercept is 0, your formula is just slope times x. But there's no y-intercept there if the y-intercept is 0. So you get a very easy formula. Linear functions like this, where the y-intercept is 0, these are called direct proportion functions. Direct proportion functions, though, end up having lots and lots of applications, so especially in science. So many quantities in science are related to each other by direct proportion functions. So when you get to a science class, and so if you are a science major, right, of some sort, or an engineering major or a math major, you're going to end up taking some science classes, you're going to encounter lots of direct proportion functions because, again, as I mentioned, many quantities in science are related by direct proportion functions. So we wanted to look at some examples here of some direct proportion functions, since they're just simple types of linear functions. sometimes when you're dealing with direct proportion functions, the slope there is, instead of being labeled m, it's often labeled k, okay? And that's just for historical reasons. But that value k is just the slope. But in the context of direct proportion functions, that value m, that slope, is called the constant of proportionality. But remember, that's just another name for slope, okay? But in this context, for historical purposes, that coefficient is sometimes again called the constant of proportionality. All right. Here's a very typical type of problem. So we'll look at this example next time. This one's kind of abstract, but it's a very typical version of a direct proportion problem. All right, so let's see what this problem is telling us, and then we'll try solving it next time. It's really easier to solve than it is to understand. Reading in the problem is the hard part, okay? Solving it is really simple. So in this description, it says some quantity y, but they're not telling you what that quantity is directly proportional to another quantity x. So if you say y is directly proportional to x, the quantity y is directly proportional to x, what does that mean? That means two things. Y is a function of x. Well, I guess three things we could say. Y is a function of x. So this is telling us y is a function of x. And it's telling us something about the function. It's telling us this is a direct proportion function. So what do direct proportions functions look like? They're straight lines, right, okay? So y is a linear function of x, but it's more than that, Arthur, because what about that linear function? What's special about that linear function? How do linear functions become direct proportion functions? What? The y-intercept is 0, right, okay? The y-intercept is 0. So what we know here from that sentence is that, y is a function of x, and the function is very simple. It's just a linear function with no y-intercept. So it looks just like that. It's a very simple formula, okay? Just a very simple formula. No y-intercept, just slope times x. But again, in this context, we will frequently label the slope rather than m, which is often the letter we use for slope. In this context, we frequently will label the slope as k, okay? And we'll refer to it not as the slope, but instead as the constant of proportionality. So the first question they're asking you is find the constant of proportionality, okay, in this particular for this particular function. In other words, find the slope for this linear function, right, based on the information that we're already given, okay. So that's kind of the type of problem here we're going to be tackling. All right, well, let's save that for next time because we want to have time to, as I mentioned, finish our the homework that's due tonight. And if you've already finished that, then get a start on. Not many of you have worked on the quiz, so get started on the quiz, okay, which is due. I moved it back to Saturday, okay. But that quiz, if you finish both those things, then you can work on into the Chapter 2 homework, all right? I'd like everyone to get 100 or really close to that homework that's due tonight, okay? So Taylor and I are going to go around and see where you're at on that. If you've already finished that, so that's 1.4 part 2. If you've already finished that homework with 100, that's great. Just verify that with me or Taylor. If you haven't, then let's continue working on that so you can get 100, all right, for that assignment.